Hi, let's start this video with a quick revisit to what was covered in my earlier videos. We saw that we need a device like MOSFET which can work as VCCS so that we can build our voltage amplifier. But then we saw that for a MOS to behave as a VCCS, we need to bias it in saturation region. We did analyze the circuit you are seeing here. We got that small signal voltage gain will be GM times R parallel R out. Also, we saw that this circuit is exactly similar with the circuit you are seeing on the right in terms of small signal analysis. We have discussed this in the last video that we need to keep transistor in saturation region so that it behaves as a good VCCS. Now let's look at the circuit shown on the right. After biasing MOS in saturation region by putting required current externally and providing enough VGS, we can see that small signal circuit can be analyzed over this operating point. We know that we have to bias MOS first and then we have to give input signal which is supposed to ride over bias voltages or currents. We can visualize this from the figure you are seeing. VGS underscore bias is a voltage source and ID underscore bias is a current source needed for the circuit to establish proper bias, which as discussed ensures the MOS in saturation region. V input is input voltage signal which we want to amplify, and output voltage is measured across drain and source. Remember that output voltage itself will have some constant DC voltage which is V out underscore bias. If you think about this in isolation, you will realize that input signal, depending on its amplitude, affects the position of bias point. Larger the amplitude of input voltage, more variation in VGS of MOS will be seen, which might result in change in small signal parameters like R out and GM. Smaller the amplitude of input voltage V input, more confident you are that the circuit will remain in saturation region, which also means that bias will not get affected much. This graph you are seeing now is of V out versus V in for the circuit we just saw. What we are doing here is we are plotting V in, which is nothing but total gate to source voltage VGS on the x-axis and VDS measured on the y-axis. When VGS is 0 volt, there is no current flowing through MOS and all the current flows through R and generates voltage of ID underscore bias times R as VDS or V out. As we start increasing VGS and VGS crosses V threshold, now the current starts flowing from R and MOS both. As we know, this current split will be totally depending on the on resistance of MOS and the value of R. Also, we know from my last video that value of output voltage will depend on R, but essentially what will happen is the current flowing through R will start reducing as you increase input voltage, and this will happen because now MOS also has started taking current. VDS will start reducing. We are only looking for a trend here, so there is no need of knowing exact numbers. It is enough to know that VDS will start reducing. Now as we keep on increasing V in, VDS will keep on reducing, and after certain value of V in, we know that MOS will start entering into linear region from saturation region. If you revisit IDS VDS plot, you will easily understand that the rate at which VDS changes for equal steps of VGS change will be higher in saturation region and less in linear region. Now let's set the biasing point of MOS in the circuit we saw some time back to the blue point shown here by applying appropriate ID underscore bias and VGS underscore bias. Now if we apply our small signal input at V input voltage source, which also can be seen as a perturbation given over the value of VGS underscore bias, we can find out how much output voltage VDS will be by projecting the same set of points around the blue point on y-axis. From this, we can easily get to know what is the value of small signal gain, which will be the ratio of amount of variation observed over y-axis to the amplitude of the voltage which we fed in, which is nothing but V input. Now what if we increase the amplitude of input voltage V input? Let's say that we are giving input swing as you can see on the graph. You can see that the output swing is not in exact proportion of input swing because there is change in operating curve of MOS if we give this large swing of input. You can see that for some values of V in, there is no change in VDS. So V out over V in equation, which is nothing but gain, cannot be written straight away. You can write this equation for the other part where V out changes as V in changes. But you cannot write it for the values of V in where V out doesn't change even if V in changes. This is exactly what non-linearity is. Also, you can see that large input swing might not only be the reason for the non-linearity. Let's say that if we set value of VGS underscore bias such that now the blue point is close to the cutoff region. In this case, even if for the small input swings given on V input, non-linearity will occur in response of the amplifier. So there can be many reasons for non-linearity. But if you think all this is coming because we can see that the MOS characteristic itself is not consistent and it has different regions where MOS behaves totally different than it does in other regions. This is the reason why MOS is a non-linear device. For example, in resistor, no matter what is the value of voltage and current is, V equal to IR will always hold true. So the resistor's graph will look like what you are seeing. Hence resistor is a linear device. Is non-linearity bad or good? Well, it depends on the usage of the device. As we just saw, we wanted MOS to work as amplifier, but because of non-linearity, for some part of signal voltage Vin, MOS didn't work like an amplifier. So having non-linearity is not good definitely in amplifiers. But non-linearity can also be called as a blessing, as only because MOS is non-linear, we are able to use it for different purposes like voltage controlled current source or voltage controlled resistor. I hope you have now understood what non-linearity means. Thanks for watching.